Hello, and thank you for joining us today for the download. These are Tech Talks by the HPCC Systems community for the HPCC Systems community, and this is episode 26. So welcome to everyone, and please let others know that you're here with us. Use the hashtag HPCC Tech Talks and let people know that you're here. And definitely ask questions. We will answer as many questions as we possibly can after each speaker. Also, throughout the presentation, you'll see several polls. We want to know what you think. So exit full screen if you don't see those for some reason, and definitely participate. We also welcome your feedback, so please rate us before you leave today. And you can visit our website for information after the event. You can look in the community Tech Talks, and it'll take you to a wiki full of information about this Tech Talk, as well as several others. And if you would like to be one of our featured speakers, let us know. Reach out to us at techtalks@hpccsystems.com, and we would love to have your participation. So at this point, I'm going to turn everything over to Flavio for our community announcements.
Thank you very much, Jessica, and as always, thank you for listening to this Tech Talk. You can see that we put quite a bit of effort into ensuring that the content is the right content for the community, and also that the community drives this content, so we cater better the interests of our listeners. So for the community announcements today, we have a number of things that are quite important and coming up. Of course, our 7.4 Gold release is out and is ready for downloads. If you haven't tried 7.2 or the pre-release 7.4 versions, or even 7.0, this is your opportunity to get into the 7 line of code. There are significant improvements. There are many new features and new capabilities. So if you are looking for any of these features, things around, for example, integration with other systems like Spark and more, you should really consider going to, at least giving a try to 7.4. It is out again, Gold. Go read the release notes, and certainly there is a link on the screen that you can use to see what's been new in the 7.4 series and, of course, in the rest of the 7 series in general. And again, if you are not in the 7 series, you are late. It's been out for some time now. The other things I want to mention is the fact that we have now the latest versions of the blogs. There are 3 very good articles in the blogs, and those are also, the links are also on the screen. Just go through them. They are, as usual, excellent, top-notch content. There are things like, for example, the new ECL features, ECLID features, I'm sorry, for 7.0, which if you haven't, if you are not in 7.0, or even if you are 7.0 but you haven't explored all of the features, that article is quite interesting. And of course the data for good one, and also the time series analysis, which is also a particularly good article. Now we did have also 2 of our sessions for our 5 questions series. One of those with Professor Koshkov Tar from Florida Atlantic University, and the other one with Josh Jane, who will be one of the presenters today. So if you haven't listened to those are very, very short episodes, as usual in this series, no more than 10 or 15 minutes. Good for a light listening on what's going on in the community, and some interesting topics on how these community members are evolving and developing new capabilities and uses for HPCC. And last but not least, and this is a very important announcement, we have our Community Day coming up. Yes, this fall, as every fall for the past 10 years, we have our Community Day event. It will be, as usual, here in the Atlanta, Metro Atlanta area. And we have already information on the portal, so go to the portal, take a look. Registration is about to open. And you can even see the agenda. The agenda is quite packed with content. You can see that we have a large number of high-quality speakers. I don't want to give away much more. Just go take a look at the agenda, take a look at what we have there. We will have also training the first day, which is a hands-on workshop. It's not just your run-of-the-mill teletraining thing. This is the real deal. You get to play directly with data and solve problems as you learn. And a poster competition. Many of our community members that some of them students, some of them not, will be presenting posters. And we have also, as part of the activities in this community day, a plan to do some changes on the way we have our external presentation area. And if you go to the agenda, you will see these changes. I think they are very positive. You will be able to interact directly with those presentation booths and different demos and capabilities. So do not hesitate if you are about to decide to go to that community day. Please consider it seriously and register as soon as the registration opens. So without much more preamble, I wanted to introduce our talks for today. We have 4 great talks. All of these presenters are community members. Some of them are interning in our program in different locations, and they are students and scholars, and aren't we all students and scholars in some way? And they are going to be covering a number of projects that they've been working on over the past couple months or 2 or 3 months as a minimum. And these projects cover a gamut of things from deploying HPC systems clusters using Juju charm to a detection of fraud in some applications for credit cards in banking industry, the evaluation of the performance of machine learning algorithms on HPCC systems, and even interfacing Octave. If you are not familiar, Octave is a very good open source project. So if you are familiar with it, well, we are interfacing it with ECL, and one of the presentations also is around this. And no more preamble, let's give the floor to our first talk by Josh James. So Josh, this is your opportunity. The floor is yours. Thank you.
Yeah. Good morning, everyone. I'm going to be talking about cluster deployment using Juju charm. So first off, let me start with the question. How experienced are you with Juju? There would be a screen there would be a poll screen which would be presented before you. Please do select the options. Okay, so let's move ahead. So what is Juju? First off, Juju is an open source application modeling tool. Basically what that means is it allows you to go and deploy nodes, deploy your applications onto the clusters. So basically it will provision the node, it will configure the node, it will go and start the application, it will go and take down the application, it will go and do everything for you. It works on multiple cloud environments. It supports AWS, it supports Google Cloud, it supports Azure, it supports local deployment through LXD clusters. Juju is basically a OpenStack project, so obviously it integrates very well with other OpenStack components. And as I said before, it augments Kubernetes. It augments Kubernetes. So basically, you'll just you'll write your Kubernetes recipes, and Juju will go and deploy them for you. So this is the structure, which is this is the general outline of what happens when you use Juju. So basically, you have a command line interface or a graphic user interface which you use to interact with the controller. The controller is kind of the main management node for the charm, and the controller. A controller can have multiple models inside it. So basically a model would be something like one cluster running. So if you have like multiple clusters running, you will have multiple models, each controlled by the same controller. So yeah, a controller is the management node. Applications are installed within the models, and they are called charms basically. So so how does Juju relate to HPCC systems? So initial HPCC systems charm was developed by Xiaoming Wang, my mentor for this project. However, the earlier version was not really maintained very well. The Juju charm code got updated. There were changes into the API and everything, which which the code did not go and reflect. So I developed the newer charm along with my mentors Ming and Kevin. The newer version works very well with the current Juju version 2.5, and it can be deployed using a GUI or a bundle. So what are the advantages of deploying through Juju Charm? So deploying, as I said before, it will go and provision the nodes for you. It will go and install the OS. It will go and change. It will go and install the packages. It will go and start the nodes. It will go and ensure communication is fine. Communication is working fine amongst the nodes and stuff. So yeah, it obviously makes your life easier to go and deploy. So it can be deployed to majority cloud environments without any code changes mostly. So yeah, and it provides a GUI to manage the nodes, which I'll go and come back to later on. So what are the disadvantages? The code is still under development, and we do not really manage persistent storage very well. You can still go and incorporate persistent storage into your charms, but it's going to be difficult to manage it at a larger scale. So let's start with the bundle demo here. So I have, let me just share my screen here. Okay. The screen is now shared. And here I have the Ubuntu node which is going and doing this. So initially when you start when you use the Juju charm for the first time, you need to go and run the bootstrap command. So Juju bootstrap will create a controller for you. Here in this case, we are going and creating a controller on AWS. And the name of the controller is the AWS controller. I have already done for you. You can see the status using Juju status. So it will go and show the controller is AWS controller. It has been deployed for AWS AP South 1. So then we go and deploy Juju deploy. We go and deploy it through a bundle. I have already created a bundle and it will go and deploy the charm for you. So as you can see, there are some commands which it's going and executing. Let's just come back to it, once it is done. So in the meantime, let me, as you can see, machines are being allocated and everything. Let me just go back to the slides here for a moment. Yeah. So AWS through charm bundle. So we are going and deploying, multiple layers of the charm can be bundled together using this. So as of now, we have created a layer for, the basic standalone charm. There's one layer for the Dali charm, and there's another level for all other charms, for Shasha, Thor, Roxy, etc. They are all deployed through the same base layer. So this allows us to reduce the amount of code which we need to write. It reduces the redundancy. And it allows us to fine tune the charm quite easily. So we bootstrap a controller already. We have deployed the charm. Now this thing will work fine. So by the time this thing is deploying, let me run through the YAML file which I have used to deploy the charm as of now. So for the standalone charm, as you can see, there's a field for description, which can be anything, which can be, as the name suggests, just a brief description of what it does and what it is. Series is the Ubuntu version which you want to use for the base layer for the operating system. It can be Bionic, it can be Genial, it can be anything. And services are the charms which you need to go and deploy into the model. So in this case, we are deploying a service called HPCC, and the charm is this CS YDGen open source. This is my private repo which I'm going and using to deploy right now. The number of units is the number of units I want to go and deploy, as the name suggests. Further, we can go and have constraints associated with every single deployment. Constraints can be, number of cores, memory, the size of the root disk which is attached, the zone which the charm gets deployed on, etc. So, and as far as exposed is considered, initially, whenever you go and deploy the charm by yourself, the charm is not exposed to the public network. So when you go and set this flag to true, it will go and make the charm available for public. So this is another YAML. This is for the cluster deployment. So as you can see, I'm going and launching one Thor node. I'm launching one DALI, one Roxy, one Thor, one support, and one of the master Thors. So let me go through them. So this is just the snippet for the top version. So as you can see, it is quite similar to the earlier one. The only difference which we do have here is we go and add relations. So relations would be something like, I have deployed these many charms, now I need to go and connect it to them. So basically Thor should know what the IP of the, DALI, Thor should know the IP of the DALI node, DALI should know IP of the Roxy node and stuff like that. So we have relations between Thor, DALI, DALI support and stuff like that. So after this is there, there's also another way which I'm not gonna be presenting right now. You go and use the command line to go and deploy this. So the command goes something like Juju deployed followed by the build charms followed by the series and the type of the node and this way. So let me see if the I think the cluster has been deployed. Let me just reshare the screen once again. As you can see from the Juju status command here, the current status, cluster.changed, master.joined, and so everything has, joined the node. So we need to go and start the cluster. So for this, we go and run the HPCC configure script. So this will go and run the, we go and run this and we wait for the results to be shown. So basically when we go and run this, the cluster will go and generate the environment.xml and every single node will get the copy of the environment.xml into it. So as soon as we went ahead and did this, every single node was automatically stopped. Then the DALI node updated the environment.xml. As you can see, everybody was fetching this thing here, and then finally this has been fetched. Now every single thing is restarting the nodes. So just wait for a moment. Starting. Yeah, everything is now started. So we can now go and visit these. These are the 3 IPs which we can go and see. So if you go and see the GUI, let me just get started. I think I lost. As you can see, there are multiple nodes which are started here. So this center one is the DALI charm, which we have gone and deployed. This is the master Thor. This is Roxy. Here is the slave Thor, and this is the support node which is connected. Now every single thing is now up. So we go and take the IP for the support node, and we go and visit ECL watch. So the ECL watch is running here. As you can see, there are multiple nodes which are attached to the cluster. If we go to the playground here, we can go and execute the query. As you can see, there are 2 nodes which are coming up. Similarly, now we can, this also integrates with other charms. So you can have MySQL. Let's just go and deploy it in the meantime. So in the meantime, we are gonna go and connect. We are gonna go and connect this cluster to our MySQL deployment. By the time this thing comes up, let me go back to my slides. And yeah, The slides are now up. So as you can see, we waited for the ready state. Then we can see this thing on the AWS CLI, and we add the relations. Since we are not deploying it through the command line, we don't have to worry about it. So we started the cluster. We ran the HPCC config command. Everything was started. Then we exposed the support node. Since this was deployed through a YAML file, we didn't have to actually go and expose the node. This thing was present in the YAML by itself. So as you can see from the command line interface, there are 5 nodes coming up, and this is the MySQL node which we have added right now. So this is the output which we saw earlier. So as you can see, the MySQL node has come up here, and we attached it to the DALI node through the GUI. So once that thing is done, we're going to see the outputs here. Let me see if the final output is available for us. Let's see. I think the screen share is not working. Okay. Anyways, as you can see, once that thing is done, we can go and add. Using the GUI is quite simple. We just click the nodes, and we just click this. We just click the node, and just drag and drop. That's it. So once we do that, we go and see the output here. The nodes are connected. This command line this GUI is quite simple to use. This concludes the demo, and let me ask you this. So are you going to use this thing in your work? I mean, so from what you have seen so far, do you seriously think that this thing is something which is worth for you? So please do comment using the poll, and let me know if you have any questions.
All right. So Yash, will you take a moment to review the questions that have come in from the audience? I'm going to review the results from your first poll. So the question was, how experienced are you with Juju? So 92% of you said that you've heard of Juju but have not ever used it. 7% have just started to use it, but unfortunately there are no Juju gods in our audience today. So, all right. Yash, I'm going to go ahead and move to the questions if you're ready.
Yeah.
All right. So here's our first question. Can I deploy this on my own OpenStack cluster?
Yes, you can go and do that. Remember, in this case, we went ahead and bootstrap using the command Juju bootstrap AWS followed by the controller's name. In your case, you'll go and use OpenStack instead of AWS, and that will work perfectly fine for you. It can be deployed on OpenStack. Yeah.
Right. Wonderful. All right. So here's our second question. How does Juju differ from Kubernetes?
Juju is quite different from Kubernetes. It goes and augments Kubernetes as such. Basically, when you go and run a Kubernetes recipe, Kubernetes will go and create the charms for you. It won't go and provision the nodes for you. So multiple pods running, and basically you have to go and manage the actual node yourself. You can have 10 machines running, and then you can go and use Kubernetes to go and deploy them, but Kubernetes will not go and run the machine for you. In this case, Juju will go and actually spawn the node for you. It will go and start up the node. It will go and boot everything and schedule everything and whatever, and then it will go and launch the application. So it kind of exceeds Kubernetes domain on that part, on that front. Yeah.
All right. Wonderful. Thank you. All right. Here's another question. How do you switch AWS availability zones using the charm bundle?
So basically, for switching the AWS zones, you are in the constraints option which you saw earlier. You can go and have options which will go and say AWS cloud type will be this, so it will go and deploy to that specific zone. In this case, this is just a demo. I deployed it on AP South 1, but you can have multiple zones present in your cluster. Sure. So next question.
Thank you. All right, so here's our last question. Is this tool only deployable from a Linux, Unix environment, or can it be used with a different OS?
Can you deploy it through a different environment? See, basically, when you go and deploy it, you can use the GUI to go and deploy it. So, till the day you can go and visit the particular GUI website, you can, go and deploy any charm which you want. If you wish to say, like, can I deploy HPCC on Windows or something of that sort? No, your Juju does not run on any other nodes. When I meant, it supports multiple operating systems, I meant, it supports different versions of Ubuntu. So it supports, 1604, 1704, whatever. Just, you just need to specify the variant name and it will go and do that for you. I hope that answers the question well.
All right, thank you, Yash. Thank you. All right, before we move to our next presenter, I want to go to Yash's last poll question, which was, could you use this Juju charm in your work? And 72% say yes. So that's fantastic. So Yash, hopefully we'll have more people leveraging this charm. And we thank you very much for this presentation today. And that was a wonderful, very instructive demo. So thank you.
Thanks a lot. Thank you.
All right, thank you. All right, so our next presentation is machine learning techniques to detect fraud in credit cards and human activity recognition. So I'm handing everything over to Akshar.
Thank you so much, ma'am. Hi, everyone. Good morning. I'm Akshar Prasad. I'm from RV College of Engineering in India. I'm currently pursuing my BTech in computer science. So first of all, it's a great pleasure for me to be presenting to such an esteemed crowd. Let's start. Well, in my summer, I actually used machine learning techniques to detect fraud in credit card transactions under the mentorship of Roger Dave. And finally, I moved on to human activity recognition after finishing this a bit earlier than expected to explore certain data sets and certain machine learning algorithms. So before we actually move on to the details, just a quick poll. How many of you actually feel safe making credit card transactions? Or even for that matter, owning a credit card? Right, while you answer, I'll just move on to the next slide. So I'm pretty sure all of you know what credit card fraud is. So just a quick recap. Credit card fraud basically refers to any illegal means of obtaining, account information and then perform some unauthorized or illegal transactions on your behalf. So this is something that's very close to identity theft. And see, credit card frauds these days are very attractive and desirable, but they're often susceptible to fraud. So it leads to a lot of privacy and data breaches. So it's actually it's the challenge for a company to detect these fraudulent transactions in a timely and effective manner. So machine learning fits in perfectly to this because one, it's an expert in detecting anomalies and it's quick. So that's the reason we have used machine learning algorithms here. Now, while I was researching about this topic, I actually came across a few tidbits that I found were really interesting. Now, the Federal Trade Commission of the United States actually studied over 12 billion transactions and found that over 10 million of it was fraud. So essentially, 1 in 1,000 transactions are fraudulent. 5% of the US citizens have been victims of credit fraud. And all this havoc is actually caused by a mere 0.04% of the monthly active accounts. So it's just a small fraction of people, causing such huge financial losses. And this came as quite a shocker to me. Your credit card details, your sensitive information is actually sold on certain card buying websites for a median amount of $27 per card. So yeah, some of the websites are Escator or there are plenty of others which have this option. Now, I'm pretty sure all of you know what techniques fraudsters use to get such illegal information, but just to give you a brief overview, they use skimmers, which are basically devices that read and store the credit card information when you make a transaction. It actually reads your data on the magnetic chip in the back of your credit cards. There's also phishing, which is where criminals pretend to be bank officials and then convince you to shell out certain information to them. You also have duplicate websites which actually try to pass off as authentic bank websites, and so you'll naturally be inclined to give out your passwords and PIN numbers to them. So now, my objective during this internship was given a series of transactions to identify and classify it as fraudulent or not. So the machine learning models I personally have used are random forests, which are more popularly known as learning trees in the HPCC systems. I've used a one-dimensional convolutional neural network and a long short-term memory. Now, coming to the data set, this data set is available on Kaggle. It's basically transactions carried out by European cardholders over a certain period. Now, this particular data set is essentially one big time series. So you can, I guess it will be clear if you look at the plot at the bottom of the slide. So it's actually a plot of the amount versus time elapsed. So you can sense that it's just one big time series, and it's our duty or our problem to get it into a fixed format to be used for a machine learning algorithm. Now, diving deeper into the data set, we can see that the time field, these are the first 5 records in the data set. The time field basically indicates the number of seconds that have elapsed since the first transaction has taken place. The amount field obviously represents the amount. Now, these V1 to V28 fields, they're actually the 28 most significant vectors after performing a principal component analysis on it. Now, for those of you who don't know what PCA is, I'll be giving you a brief intuition in an upcoming slide, so please bear with me. Then we also have the class field, which is basically a Y vector. The 0 represents a non-fraudulent or a legitimate transaction, whereas the 1 indicates that it's fraudulent. Right, now the models that have been used, I'll just try to give you a brief overview of it, some intuition or some sense of what's happening. Now, random forests, or more popularly known as learning trees in the HPCC system, they're basically an ensemble of decision trees. Now, decision trees are tree-like structures where the internal node tests a subset of the input features, and based on that, it tries to send it down to a suitable child node. And the leaf node actually is the ultimate classification of it. Just for your reference, I've added a simple decision tree at the bottom of the slide. So this decision tree basically decides whether a person should play golf or not. So you can see that the root node over here, it actually tests the weather. Now, if it's cloudy, it sends it straight to the yes leaf node, so it's classified as a yes. If it's sunny, it's sent down to the left child node where that checks the humidity and so on. So that's how decision trees work. Now, the objective in a decision tree is to train the, the internal nodes to make sure that it tests the right input feature and then sends it down the right path to ultimately to the right classification. Now, in random forests, what happens is we have, say, just for this example, let's take there are 10 decision trees. So now each decision tree is actually trained on a random subset of input features. Now, we wouldn't want to give each tree all the input features because then we'd end up with 10 identical decision trees, which is not desired. So we get certain, we take certain subsets, train each decision tree. Now, if we have to, in a task of classification, what we do is we get the classification of each decision tree, put it to a vote, and the class with the highest number of votes is the ultimate classification. Now, coming to regression, you'd probably consider taking some kind of average of all the outputs and get a final output. So this is how random forests work. Now, coming to one-dimensional CNNs, this is a beautiful algorithm, and I would have loved to go into the depth of it, but due to certain time constraints, I wouldn't be able to. But to give you a difference, an intuition about how one-dimensional CNNs differ from the two-dimensional ones. See, in a two-dimensional CNN, your input would essentially be one 2D image or any two-dimensional sample. So you would have a small kernel that would actually iterate through the image as shown in the figure to your right. So it would essentially be like looking at a dark image with a flashlight. Coming to the one-dimensional CNN, you would have a the kernel would cover the entire feature set of a time step, but it would cover multiple time sets at a time. So that's the essential difference. There are certain tweaks here and there, but this is essentially how one-dimensional CNNs work. Right. So one-dimensional CNNs actually thrive or specialize in certain places where the temporal locality is not of the greatest significance. In the sense, there's a lot of memory is not required. So this would particularly be seen in natural language processing or some short signals that you have. Right. Moving on to LSTMs. Now, long short-term memories are actually a variant of recurrent neural networks. The disadvantage of recurrent neural networks is, you see, when you have a recurrent neural network, you have a very high risk of exploding gradients or vanishing gradients happening. Case of such cases. So that's why LSTMs were invented to cut this down and to help have a greater memory in each node, and to make sure that that the gradients are it doesn't explode or it doesn't vanish. Now the input to the LSTM is the current time steps features and the previous output. So each node actually has a memory cell and 4 neural networks to train the memory cell to determine how much memory to retain, how much memory to adapt to the new time steps features, etc. Now I would have loved to explain the architecture, but again, because of time constraints, I wouldn't be able to. So please feel free to ask me these questions in the Q&A if you're further interested. I would love to explain these models. Right, now this is something that I tried out during my internship, which was really interesting. Roger Dave actually has a new bundle coming out, Generalized Neural Networks. Now this basically provides an ECL interface to Keras over TensorFlow. So it actually provides all parallelized TensorFlow or Keras operations in an HPCC systems cluster. Now basically how this would go about is models are created on each HPCC system node, whereas the training, evaluation, predictions are all done in a distributed fashion across all nodes, and would finally come back to the master node for updation. Now, GNN is actually, for those of you who know the sequential model, Keras' sequential module, you'd be pretty familiar with this. It can handle any neural network model. It could be a classical neural network model, a dense layer, to even as something as complicated as a long short-term memory network. In fact, you can also use a combination of networks over the sequential model. So that's a great addition to HPCC. It's still in its alpha version though, so it would be available to everyone. It will be available for everyone to use very shortly. Right, now coming to the pre-processing that has been done on the dataset. Now, see, principal component analysis in its essence is a dimensionality reduction technique. So the objective of principal component analysis would be, given a certain data set with some amount of dimensions, to represent the exact same data set with smaller number of dimensions without much loss of information. So I guess this figure gives you a very good intuition. You can see the plot on the left, it actually represents certain data points in a 3-dimensional space. But if you see, all the data points are actually, aligned on that particular plane, which is represented by PC1 and PC2 axis. So if we could somehow project the entire space or entire data point set onto that particular plane represented by PC1 and PC2, we would essentially be presenting projecting the entire data set in a 2-dimensional space, and you wouldn't be losing much information in the process. Now PCA is an excellent technique to use when you have hundreds of dimensions with a lot of covariance between each of the dimension. The mathematics behind this would be the use of eigenvalues and eigenvectors, but again, I wouldn't want to go into so much depth. Another major step in pre-processing is the reconstruction of the dataset. So see, our ultimate aim is to classify a small series of transaction given, right? So this one big time series that I said the time series was having, 284,807 time steps. That has to be broken down into smaller. It has to be broken down into smaller time steps or smaller samples. So what I have done here is I've broken down this time series into n number of samples having 4 time steps each. Now each time step has 29 features each. Now these 29 features are the ones that I explained, where it has the amount and the principal components, etc. So in the case of learning trees, this two-dimensional input has to be flattened out because the learning trees don't support two-dimensional inputs. Now oversampling. This is something very critical, a very critical step in the training of the model. Now, if you go back into the data set, as I said, it has 284,000 and odd examples or samples. But in this, just 492 of these transactions are fraudulent. So that's the level of skew that we're dealing with here. It's a highly imbalanced data set. So we need to tread very carefully. We need to, even when pre-processing or training the model, or even for that matter, when we are evaluating the model, we have to keep in mind that there are an ocean of zeros and very few ones. So oversampling is one such technique to overcome such cases. Now, see, if you blindly give the same data set to the model to fit it, it would obviously be biased towards predicting a zero because it has only seen instances of zeros majority of the times. And that would not be the best performance, not the desired one at least. So what we do is, one of the techniques used is we just blindly repeat the fraudulent transactions. So if in the data set, if we come across any particular fraudulent sample, we just append it to the database again. Now doing this, again, the downside would be that the model would tend to overfit the fraudulent cases. That is, it would tend to by heart the fraudulent cases. Again, this is not desirable. So what I have done is, I've added a random 10% noise each time I append the fraudulent transaction. So in this way, it sees more cases of fraudulent transactions. In the meantime, it's not the same over and over again, so there's no risk of any sort of by hearting that can take place. Right. So this is just to give you a summary of the pre-processing. You can see that after the principal component analysis has been done, there's reconstruction of the data set. Finally, there's again, this what I've done is there's also a blind appendation to the data set. There are the fraudulent cases are repeated some number of times, and later 10% addition has been done to again ensure that there's no overfitting. Now the system architecture is similar to any model that you'd have come across. There's pre-processing, you split the data set, you train the model on the training data, you get the prediction and evaluation for the test data. Finally, there's some hyper-tuning that you can do to get that 1 or 2% increase in accuracy with the same model. So there's nothing unique about this. I follow the same procedure. Right, now the evaluation metrics. See, accuracy is not at all a good metric in this case. Usually people prefer to go to accuracy, but let's just assume that this model is, it predicts every transaction to be, non-fraudulent. Now, only 0.4% of the data set is actually fraudulent, or there are fraudulent cases. So if you give the data set or the test data set to the model, and it predicts that each of it is non-fraudulent, you would still be getting a 99.6% accuracy, which to any person or any machine learning specialist would be an amazing accuracy. But in actuality, the model is not performing well. In fact, it's a disastrous model. So accuracy is very misleading in this case. So what I've decided to use are the three metrics that I'm using are precision, recall, and F1 score. Precision is basically true positives by the predicted positives. That is, I'm asking the model, out of the positives that have been predicted, that is, out of all the transactions that have been predicted as fraudulent, how many of it is actually fraudulent? Recall is basically the number of true positives in the total number of positives in the data set. That is, I'm asking how many transactions have been classified as fraudulent in the total number of transactions that are present in the data set. So F1 score is basically the harmonic mean of precision and recall. So we ultimately use the F1 score to judge the model to get a good trade-off between the two. Right. So coming to the results, we can see that LSTMs surprisingly perform, although it does give very good results. It actually gives an F1 score of 96.40%, which is great for any model. It does perform the least among the three, least well. So CNNs give amazing results. It actually gives a 99.39% F1 score, which is by far exceeding any of the models. But learning trees, CNN is a fairly complicated algorithm and pretty time consuming, whereas learning trees are much more simpler. But you can see that learning trees actually takes over the CNN by just 0.5, 0.6%, but still it does give a recall of 1. That is to say that all the fraudulent transactions have been successfully predicted as fraudulent. There are some false positive cases, but it does give an amazing result. Just to tell you that all of these are test accuracies or test scores. It's not on the entire data set or not only on the training set. So yes, we did get very good results. Now, just to give you some intuition about why this is happening. Before that, I just want to iterate through the power of HPCC. Now, the time taken without using HPCC, when I augmented the same code in Python, it actually took over 1.5 hours. But with HPCC, I was done within half an hour. And another thing, the results as well, I did find that there was a slight improvement in results when I used the algorithms, available within the HPCC systems. So HPCC systems have just been great. Right. Just to give you some intuition about why random forests or learning trees are performing outstandingly, whereas LSTMs are failing. Now, the LSTM basically thrives when there's a long time series, where there's a lot of memory that's required and the temporal location is of great significance. Whereas, like I said, CNNs, they do not give a lot of importance to the temporal location. So in this particular data set, from this results, maybe we could infer that the temporal location of each transaction is not of the greatest significance. So the use of CNN is giving us the 3 or 4% extra accuracy that we want. But the surprising thing is learning trees is actually performing marginally better than even a one-dimensional CNN. So the reason for this is pretty simple. Now, learning trees, one, they do not overfit the data at all. It has the least tendency to overfit the data because, as you can see, we have actually taken a subset of the input features. So there's very little scope for any overfitting to take place. And another thing is, each tree covers for each other's mistake. Now, again, we could go back to the wisdom of crowds, where the entire crowd wouldn't make a mistake, but rather each person would cover for each other's mistake. So if, say, we had 100 trees, for this particular model to give a wrong classification, more than 50 trees should be giving a wrong result. But usually it's not a lot of error takes place, so the rest of the trees cover for the trees which give the wrong values. So this is probably why learning trees perform way better than even an LSTM or a CNN. So right, this is my conclusion. Now a quick poll. Now, do you actually feel safer with such algorithms, guarding your money in the sense? While you give your answers, I just have another thing to cover, which is the human activity recognition. Now, I'd completed this part of my internship much earlier, so we wanted to get one data set and test it out where there's a lot of temporal significance. That is, it's a proper time series with a lot of significance given to each time step. So we actually opted to use human activity recognition data set. Now, human activity recognition is basically the problem of predicting what a person is actually doing based on a trace of their movements using some sensors. So my task was, given a sequence of accelerometer data recorded by some smartphone or any specialized harness for that matter, into some well-defined movements. Now here I've again used learning trees, LSTMs, and one-dimensional. I've used a one-dimensional CNN followed by an LSTM, which was the first time I've been using this, so it was very interesting. Right, so the data set is actually collected by 30 subjects wearing some waist-mounted sensors. In this case, it's their smartphones. So each of them is performing one of the 6 standard activities that is shown on your screen: walking, walking upstairs, downstairs, sitting, standing, and laying. And also the video of each subject was recorded to manually classify it at a later stage. Now the data set now the data set essentially consists of the XYZ axis of the accelerometer data. Now this could be the linear acceleration as well as the angular velocity, that is the gyroscopic data. Just for your information, this was recorded at a right. So certain pre-processing techniques that have been used. Just to iterate, these pre-processing techniques are not done by me. This was readily available. The pre-processed data set was available to me. But just to give you an intuition, one, there were certain noise filters that were used to pre-process the accelerometer and the gyroscopic data. Again, there was a reconstruction of data set that was required. So we essentially broke it down to 2.56 seconds with 128 data points each, and there was a 50% overlap. Also, the accelerometer data was split into gravitational and body motion components. Gravitational is your downward acceleration, whereas body motion is your linear or your horizontal acceleration. So essentially, what I ended up with was a 3-dimensional data set. So it had to be distributed across files. What we had at the end, we had 128 time steps in each sample, and each time step had 9 features each. So just to reiterate, the 9 features were the XYZ axis of gravitational and body accelerations, as well as the gyroscopic data. Now this has to be uploaded onto the landing zone. So I did write a program to flatten all this data set and upload it onto the landing zone of PCL. So I've gone through the other models, but this one-dimensional CNN followed by LSTM was pretty interesting. The CNN LSTM architecture actually involves using a one-dimensional CNN for feature extraction on the input data, and this data is actually combined by LSTM. It analyzes these extracted features as a time series and gives a prediction. So the CNN layer, what it does is it will read subsequences of the main sequence as blocks. So it extracts feature from each block, and it then allows the LSTM to interpret these features for each block. That is, it treats all the blocks as one essential time series. So there's these 128 time steps in this particular case has been broken down into 4 blocks of 32 time steps each. So right. So just to give you the results, learning trees were actually not very suitable for this case, but I included it just to show you the contrast. So it actually has a power accuracy of 84.356%, whereas the LSTMs, which again specialize with longer time series, gives an excellent accuracy of 93.034. Now note that this is a multi-classification with 6 output nodes. So getting an accuracy of 93-94 is it's a very good performance by the model. Now the one-dimensional CNN followed by LSTM gives us that slight 2% edge because of the features extracted by the CNN. So finally we did end up getting an accuracy of 94.717 with the help of HPCC. So right. This is my presentation. This is the work I've done. I just want to iterate that I've cherished each and every moment working for HPCC, and I would love to continue to use it on any other projects that I do from now on. So thank you so much. I'd like to thank my mentor Roger Dave again, Lorraine Chapman ma'am, and Trish Mikhail ma'am. Thank you so much. Thank you all.
All right, thank you. This has been a wonderful presentation. So Akshay, while you go and review the questions that have come in from the audience and prioritize them, I'm going to review the votes from the audience for your first poll question. And so that first poll question was, do you feel safe making credit card transactions? So 58% of you said yes, and 41% said no. And since we've had plenty of time since the last poll went through, let's look at that one. So that question was, do you feel safer with such algorithms guarding your money? And 76% say yes, and I totally agree with that. There's a lot of very good information in here. All right, so we're going to go ahead and take a quick peek at the questions that have come in. Are you ready, Akshar?
Yes, ma'am.
All right, perfect. So the first question is, what was your experience of using HPCC systems?
Yeah, thanks for that question. Yes, initially when I got into HPC, when I explored HPCC systems, it was pretty daunting. I had to learn a new language. I had to learn how distributed systems work. But as I actually started working on it, I used to appreciate it every day because of the computations that take place, the amount of complexity that goes behind the scenes. I used to appreciate it every day, and again, like I said, the results that I got, the speed that HPCC provided, it was amazing. So I had an excellent experience working with HPCC systems.
Fantastic. We're really happy to hear that. All right. Here's another question. What made you use random forest? Was there a particular reason that you chose that?
Yes. Yeah. Very good question. Yeah, I did. When I actually explored the data set, there was I had the fear that there was going to be a lot of overfitting because there were a lot of samples and a lot of features. So there was a high risk of overfitting. So random forests, they're one of the least likely models to be, for any kind of overfitting to take place. So I actually wanted to try learning trees or random forests, and but to be honest, I didn't expect it to give such great results. I didn't expect it to overperform even a one-dimensional CNN, and it was a pleasant surprise for me to get that result.
Okay, perfect. All right, here's another question for you. Can you tell us the exact parameters used in the three models?
Oh, yes, definitely. Yeah, thank you for that question. Now, in learning trees, I used 32 decision trees with a maximum depth of, again, 32. I did a lot of permutation and combinations, and I got the best results with this particular hyperparameters. Coming to the one-dimensional CNN, in the first layer was a one-dimensional CNN, obviously, with 64 filters. 20, the kernel size was 20, yeah, it was 20 with an activation of ReLU. There was a dropout layer I used to avoid overfitting. It was followed by a one-dimensional max pooling layer. I think I used a pool size of, I guess, 2. And then there was a flattening layer, and finally a dense layer with a sigmoid activation to sum it all up and give us a binary classification. LSTMs, see, the thing about LSTMs is, it's not recommended to use multiple layers of LSTM, but because it may be giving you a 0.5 or a 1% increase in accuracy, but in the process there will be a lot of computational, it would be computationally expensive, but because I was working on HPCC, I had that freedom to actually add that second layer of LSTM and get better results. So I essentially used 2 layers of LSTMs with, I guess, 32 nodes and 16 nodes each.
Okay, thank you. Here's another question for you. I see your data is highly imbalanced. What technique have you used to deal with the imbalanced data?
Yes, yeah, it is highly unbalanced. I was dealing with a lot of skew. So the first thing, like I mentioned in my presentation, I used oversampling. But see, even if I oversample it, I can even if I append it blindly, say 10 times, I would still not get a good balance between the two. I would have to, balance it multiple times. So I actually opted for a small variant of data augmentation where I randomly added noise to it and made sure that it wasn't repeated, but it was still seeing certain instances of fraudulent cases multiple times, so that the bias towards zero would, we would avoid the bias that the model would essentially take. Also, in the accuracy evaluation metrics, I had to use different parameters, different metrics, like I said, precision recall and F1 scores.
All right. Okay. So we have one last question here, and it's, well, actually we have several, but I can only do one more. The question is, can you please explain the use of memory cells in LSTM?
Oh, yes, with pleasure. I was actually hoping someone would ask this question. If I have enough, can I take another couple minutes to explain this?
Yeah, absolutely.
Sure. Then I just like to go back a couple of slides to get the architecture of LSTM. Right. So if you can see this architecture, there are 4 neural networks and 1 memory cell. Now the input to this particular is the current features, the current time steps features, and the previous output. So now the neural network to your right, which has a bias 0, as you can see, that is called the forget valve. Now what this particular network does is it trains these, it trains itself to output how much of the data, how much of the old memory should influence the new memory. So you can see that it has a sigmoid activation function, so you would essentially have an output ranging from 0 to 1. So this particular output is multiplied with the old memory and added to the new memory. So say for example the model says thinks it's apt to remember say 20% of the old memory. This particular model would give an output of 0.2, which is multiplied with the old memory and then added to the new memory. So the old memory is actually there's a network to using a tan H activation function. The second the network with bias 2, you can see it actually is the old memory that has been input. So there's a tan H activation function which actually has to go into the cell. You also have a third neural network which trains itself to give us the fraction of the new memory that has to be influencing the memory cell essentially. So you would multiply that with the new memory, multiply the forget valve's output with the old memory, add all of it, and that would be the input to your memory cell. So that's how memory is maintained. This is similar to a human brain, where we actually decide how much of your old memory to retain, and as new memory comes in, we tend to forget the old one while retaining part of it. So that's the intuition behind memory, the memory cell. Now again, the output is again a variant of the memory maintained in the memory cell. So use a tan H function and a fourth neural network to determine what fraction of this tan H activation function to be given as the output of this particular architecture. So I guess this would be the a general intuition about the architecture of LSTM.
All right, thank you very much. That's a wonderful answer, very thorough. Thank you so much for this presentation. This has been very good. All right, so as we forward the slides,
thank you.
Yes, of course. And our next speaker is Surya. He's joining us to talk about machine learning and evaluation metrics. We have just a few more slides to go through. There we go. Perfect. All right, Surya, you're up next. Thank you.
Thank you. So hi everyone, my name is Surya. I'm a student at RBC, and my summer project was about creating new machine learning evaluation metrics for the HPCC system's machine learning bundles. So a quick poll before we just jump in. Have you ever used the unsupervised learning, which is the k-means clustering bundle? So let me know while we move on. So for those of you who are new to machine learning, let me just give out like a brief introduction about machine learning and machine learning evaluation models. Of course, Akshar's previous talk introduced machine learning quite a bit and delved into a lot of depth. But yeah, so machine learning involves is a problem-solving approach where we use existing solved problem examples, and we find patterns in those solved examples, and we use those patterns to solve new problems. So it's a very oversimplified version or oversimplified explanation of machine learning. So of course, because of the way this process is structured, it doesn't always produce the right answers. So it's essential for us to be able to evaluate the model in as many ways as possible. So, since the evaluation of the models is so important, it's important that we have a lot of different methods that can help us evaluate these models. So these evaluation methods can help us create models that are better suited for for many situations. And since these models that we have don't just rely on the data that's given to them, and they also rely on other parameters, which are the hyperparameters of the model, it helps us tune these hyperparameters to better suit our situation and give us a better accuracy or give us better results. Also, if we have two different machine learning models, we can compare these models to know which of these models is performing better and which of them is better suited for our use case. So evaluation metrics help us do all of these things. So this is a brief summary of the already available evaluation metrics in the HPCC system machine learning bundles. So there are different machine learning evaluation metrics for different types of machine learning models. So for classification, we have accuracy and accuracy by class, which is precision and recall. We have the confusion matrix and n-fold cross-validation. And for regression, we have the mean squared error, the R-squared error, and ANOVA. So all of these are very popular metrics for regression analysis. And for logistic regression, we have deviance analysis and null deviance. Now, as you may have noticed, there aren't many evaluation measures for clustering or for feature selection. So for unsupervised learning, which is clustering, we don't have examples, or we don't have solved examples for the data that we have. So the data that we have is not labeled. So it becomes quite difficult to evaluate models that work on unsupervised or unsupervised learning models. So there was a scope for addition of clustering evaluation metrics and for feature selection. And so these are the evaluation measures that I have been implemented during the course of the summer. So the first metric is F-score, which is a very common metric, which of course Akshar also used for evaluating his model. Then we have Hamming loss, which is used for multi-class classification. And then another very popular metric, which is often cited in literature, which is area under the receiver operating characteristic curve, which is used for classification analysis. And then we have silhouette coefficient, which is for clustering. And we have adjusted rand index, which is also for clustering. And then for feature selection, we have an interesting statistical test called the chi-squared test. And to facilitate this test, we also have the contingency table, which is a general utility that can be used to study data. Okay, so a quick run through of these different evaluation metrics and how they were implemented. So the balanced F-score as Akshay had already shown before, is the harmonic mean of the precision and the recall. So this is a fairly standard evaluation measure, and it was implemented into the analysis, classification, and classification by accuracy function that was already present within the machine learning bundle. And so it didn't require a lot of designing to implement, because the function already existed, and it was just incorporated into this function. Similarly, Hamming loss, which is the number of samples which are misclassified in multi-label classification. And so while performing multi-label classification, accuracy might not be a great measure, because the number of samples that are classified, there may be a lot of classes, and the number of samples that are correctly classified may seem to be small when compared to the number of items that are not classified correctly. And so the number of samples misclassified might give a better idea of how the model is performing. So it is equal to 1 minus the accuracy. And it was implemented into the accuracy function, which is present in the classification module. And again, this did not require a lot of designing, because it was already implemented into the function. Next, we move on to area under the receiver operating characteristic curve. Now, the ROC curve is a plot of the true positive rate versus the false positive rate. So this diagram represents the ROC curve. So the true positive rate essentially is the proportion of samples in a class that are correctly classified. As in, it's the ratio of samples that are correctly classified to the total number of samples in a class. And the false positive rate is the proportion of samples in the class that are not correctly classified. It is the number of samples that are not in a class that are incorrectly classified to the total number of points that are not in the class. So when we plot these two parameters with changing thresholds, we obtain the ROC plot. Now, threshold is a parameter that's used when a classification model outputs its prediction as a score or a probability that that specifies whether a sample is part of a class. So the threshold basically tells us whether the probability is high enough for the sample to be considered a part of the class. For example, if the threshold is say 60%, and a sample has a 55% probability of being classified into a class A, then it will not be classified as a part of A, because the threshold probability is 60%. So since the ROC plot covers all threshold values, we can study the plot to understand what the best value of the threshold might be. Now, since the ROC plot gives us like an overview of all the thresholds, the area under the ROC curve is a measure, is a good measure of a classifier's ability to determine whether a sample belongs to a class or not. It is a measure of how good the classifier is at distinguishing between classes. So this area under the ROC curve can be used as a measure of how good a classification model is. Now, this while computing the area under the curve, it is much easier to note that the area under the curve is also equal to the probability that a random positive sample is ranked higher than a random negative sample. So instead of trying to plot the curve and take the area under the curve, we can simply find the probability that a positive sample is ranked higher than a random negative sample. So the implementation of the area under the curve takes the classification scores or the probability that a sample belongs to a class as the input, And also, the implementation supports multi-work item operations, which is when we want to train multiple models for different sets of data, instead of taking all the different data and running it one by one, we can give them multiple work item IDs, and we can call them using just one function, and we can get the output of all. We can get different models at once. It's also called the myriad interface, and so you can use the implemented area under the curve function to get the area under the curve for many models at once. So this is the basic overview of the design of the area under the curve function. So it takes as the input the classification scores, which is the probability or the confidence per class that a sample belongs to a class, that a sample belongs to a class. And it also takes the actual value, actual predictor labels, which are the labels into which the sample has to be classified in actuality. So the area under the curve function returns the AUC score per class, per classifier, per work item. So it also supports multiple classifiers at the same time. Next, we move on to silhouette coefficient. So since clustering is an unsupervised learning algorithm, in the sense that we might not always have the ground truth values or the actual labels of the data that is provided, we do not really know if our model is performing well, if we don't have the ground truth values into which the samples have to be classified in actuality. However, we can evaluate the model through just its inherent performance by seeing how good the clustering is, by assuming how good clusters should be, in the sense that we can find out how closely a point is related to all the points within its own cluster, and we can see how closely the point is related to all the points in its neighboring cluster, and we can compare those two values to find out if the clustering is actually doing a good job of separating these points. So the input to this function is the sample features and the predictor labels, and so since the analysis of clusters is a completely new evaluation method, it was implemented into a new module called analysis.clustering. So also following the approach taken by scikit-learn, a popular machine learning library in Python, there are two variants of silhouette coefficient were implemented. So one version gives the silhouette score per sample, and the other version gives the average score of the entire data. Also, since this evaluation method does not require the use of ground truths, it is an intrinsic clustering evaluation method in that it does not require any external data other than the samples and the predictor label. So this is a quick glance at what the silhouette coefficient will look like if it is visualized. And the silhouette coefficient can be calculated by first finding the average distance of the samples from its own cluster and the average distance of the samples from its neighboring cluster, and then feeding it into the equation to find the silhouette score. Now, this is the design of the silhouette score function. So this is the design of the sample silhouette score, which gives the silhouette score for each sample. Now, the first input is are the samples or the data points, which should be in the numeric field format, which is the format for most operations in the machine learning models. And the second input that's required are the cluster labels, which are the labels that the model has predicted for each of these values. The silhouette, the function returns the silhouette score per sample per work item. Again, this function supports multi-work item. Next is the average silhouette score, and the design is similar except for the return value, which is a single silhouette score per work item, which is the silhouette scores for the entire model, and supports multiple work items. Now we move on to the adjusted rand index, which is another cluster evaluation measure. But this time, adjusted rand index uses is an extrinsic evaluation method. In that, it uses the ground truth labels of the data to find whether the clustering is good or not. Also, since the adjusted rand index just takes the labels produced by two different clustering models, it can also be used to compare two different clustering models and see how much one differs from the other. So the adjusted rand index is a kind of accuracy, in that it tries to see how close one labeling is to another labeling, and it tries to give a value to that measure. Now, the adjusted rand index is a corrected for chance version of the original rand index, in that the corrected rand index does not give a high score for random clustering. So if a clustering algorithm tries to produce a random set of labels as an output to the clustering data, the adjusted rand index takes care that such kinds of clustering labels are not given a high rand index, which wasn't taken care of in the original rand index algorithm. So the adjusted rand index uses the contingency table of the data to find the expected rand index and the original rand index, and then compute them to find the total rand index. So I'll talk more about the contingency table later. But so this slide here shows how the adjusted rand index is calculated. So the calculation of adjusted rand index involves three major sums. The first is the sum of all the elements in the contingency table. Then it also involves the sum of each row of the table and each column of the table. And these are taken and put into the equation shown in the slide, and the ARI is calculated. So the design of the ARI function takes two different clustering labelings. So the input shows one is predicted and one is actual, but these can also be labels predicted by two different models. And the output of the adjusted rand index function is the ARI per work item. So now we move on to the chi-squared feature selection test. So feature selection plays a very important role in machine learning. It helps us filter out the unwanted noise features that may be hindering the performance of the model. So the chi-square feature test is a statistical test that we use to establish the dependence of two categorical variables. So in this test, what we first do is we establish a null hypothesis or a hypothesis that we try to disprove, that the two variables are independent. So then we try to create, or we try to find out how the data should be arranged if that were actually the case, if the two variables were actually independent, and then we test the actual data with the expected data, and we find a value, which is the chi-square value, and then we find the probability that the two variables are actually independent. And so we then get a probability that the variables are dependent. And so if we rank all the features by how or by the probability that they're dependent on the final classification value that we're trying to fit it to, we can rank the features so that we get the best features on top, and all the noise features can be filtered out. So the input to the chi-square feature test are two discrete field data sets. Discrete field is, in the machine learning production model, is a representation of many categorical variables. So the chi-square feature test function produces the chi-square value and the p-value for each combination of feature and classifier. So with the single run of the function, you can create the chi-square values for multiple features as well as multiple classifiers at once. So again, since feature selection is new in the bundle, it was implemented into a different module called feature selection under the analysis bundle. So this is the design of the chi-square feature test. So it takes two discrete field variables. One can be the features and the other can be the sample. So we try to find the dependence find the probability that the features and the samples are dependent on each other, and we rank the features according to the probability. And the output of the function is chi-square result, which is the chi-square values and the degrees of freedom for each combination of feature, classifier, or work item. Next is the contingency table. So the contingency table is a utility function that provides a representation of the frequency distribution of the combinations of two different categorical variables. In that, it provides the number of samples that each combination of classes have in two categorical variables. So it provides a way to study the data that we have in an easier way. So the contingency table was mainly implemented because it is needed for the adjusted land index and the chi-square feature test, but it is also a very useful metric to have. So it is implemented under the analysis.feature selection model. So the design of the contingency table is as shown. So it is it's the same as the chi-square feature test. So it takes two discrete field values signifying two different variables, categorical variables, and the output of the contingency table is the contingency table for each combination of sample and feature. So the contingency table is arranged in the form of not a matrix, but a single table where which has two columns saying feature and classifier, and then it has two more columns which are the combinations of classes within these variables, and then it has a column for the count of the number of samples present for each of these combinations. So these are the new data types that were created, or the record types that were created to facilitate the implementation of the new functions. So the first is the chi-square result record, which has, apart from the work item ID, the feature number, the sample number, the number of degrees of freedom, the chi-square value, and the p-value. The ARI result, which has the work item ID and the value. The sample silhouette result, which is the silhouette score per sample. It has the work item ID, the record ID of the sample, and the value, so as in the sample silhouette score value. Then we have the silhouette result, which is the average silhouette score of the total data set. It has the work item ID and the silhouette score. And then we have the contingency table. As I described before, it has the work item ID, so even the contingency table function supports multi-work items. It has the feature number, the sample number, which is just the different features and different classifiers, and the feature class and the sample, and the count, which is the number of records present for the combination of feature class and sample class. We also have the AOC result, which has the work item ID, the classifier for which the AOC is found, and the class for which the AOC is found, and the AOC. Also note that though AOC is typically used for binary classification, it can also be extended to multi-class classification, and so this implementation of AOC supports multi-class classification. So those were the output result structures that were created to facilitate the implementation. These are the new input parameters that were created. So first you have cluster labels. Although labels for the cluster is already defined in the k-means bundle, we also need this type in the ML core module, because the ML core module cannot have a dependency on the k-means bundle. So the type was also redefined over here. Next we have classification scores, which is the probability that a point or a sample belongs to a particular class or particular classes. So it has the work item ID, the record ID of the sample, the classifier ID of the sample, the class whose probability is being described, and the probability. Okay, so now we have a few tests and visualizations of the tests, the evaluation measures that were created. So the testing was performed by comparing these implementations with scikit-learn's implementations. So scikit-learn is a very popular Python machine learning library, and the visualizations show how these evaluation measures can be used to evaluate your model and change your hyperparameters. So these are just the tests on the silhouette coefficient. So it supports multiple work items, and you can see that the results match perfectly with scikit-learn. Similar results for adjusted rank index. It has multi-work item support, and the results match pretty well. These are the tests for the chi-square feature selection. So as you can see here, it supports multiple classifiers, multiple features, and it provides the number of degrees of freedom, the chi-square value, and the p-value feature and classifier. And as you can see, the results match quite well with scikit-learn's results. And these are the tests for AAC. So assuming we have 3 classifiers with 3 classes each, we have the area under the curve for each of these classes, for each of these classifiers. So these are the visualizations. So these are some of the ways in which we can use the new measures to help tune our models. So on the left we have a graph showing the silhouette score for different values of k in k-means clustering. And so you can see that the silhouette score is highest for the for k value of 2, and it keeps decreasing when we increase the value of k. So we can use this as a hint that the data intrinsically has 2 clusters, and we can go for using a value of 2. On the right side, we have an a visualization showing the sample silhouette scores at k equals 2, and you can see that all the samples have quite a good silhouette score at k equals 2. Next, we have a visualization on AUC. So this is just a demonstration of how we get better results when we use more training data. So on the left, we have a plot of how the model performs under AUC for 300 samples in training data and 200 samples of test data. As we move further along the plot, we have 400, 500, 600, 700, and 800 samples for training, and we can see that the AUC consistently increases for every class. So this is just a demonstration of how AUC works. So this is a visualization of adjusted land index. Again, since we might not always have the ground truth labels for the data that we're using, ARI might not always be useful. But when we do have the ground truth labels, it's always the easiest to use ARI to compare our clustering results to the ground truth values and find out how close we are to the actual values. So the plot on the left shows how closely related the different clustering samples, different cluster labelings are for k equals 2. So the plot shows the ARI of the models where we have the combination of k with k equals 2 with k equals 2, k equals 3, 4, 5, and 6. And as you can see, as we keep increasing k, the models become less and less similar. And you can see a similar trend for different k values. On the plot on the right, we have the ARI for different k values measured against the ground truth labels. So you can see that the ARI is highest when k equals 4 according to the ground truth labels, and it keeps decreasing when we make k either smaller or greater. So the plot on the left shows us how we can compare 2 different clustering models, and the plot on the right shows us how we can use ground truth values to evaluate our clustering model using ARI. So that's the end of my presentation, and before I wrap up, just a quick poll. Which do you prefer while assessing your model? Do you prefer using metrics and numbers, or do you prefer using visualizations to evaluate your model? So that's the end of my presentation. Thank you, everyone. Questions?
All right. Thank you, Surya. So while you take a quick peek at the questions from the audience, I'm going to warn you that we're really tight on time. So we have several questions in there. If you could maybe just pick one of them for us, that would be great. We need to make sure we have enough time for our last speaker. So while you do that, I'm going to go ahead and take a quick look at your first poll. And that question was, have you ever used the unsupervised learning k-means bundle? And 90% of you say no. and 10% say yes. So hopefully you've learned something in here as we've gone through this presentation that you can bring into your work. All right. All right, so here's our one question for today, and I do apologize because there are several questions in there. We're just running a little short on time. The question is, these evaluation metrics were tested only using k-means algorithm. Can they be applied to other clustering algorithms as well?
Yes, so that's a great question. So though these are only tested using the k-means model, they can always be used on any on the results of any clustering algorithm that may be implemented in the future. So since they only require the results of that can be produced by any clustering algorithm, and they only require the samples themselves, yes, they can be used for any other clustering algorithm.
All right, wonderful. All right, just super quick before we move on, we've had a few votes come in here for your second poll question, and that is, which do you prefer when assessing models, metrics, or visualizations? So it looks like metrics is 25%, 50% is visualizations, and 25% prefer both. Very interesting. All right, so we're going to move on to our next presenter, and that's Satvik, who's coming to talk to us today about interfacing Octave with ECL. All right, Satvik, over to you.
Hello everyone, my name is Satvik. I'm from RVC Bengaluru. Today we're going to talk about I'm going to talk about interfacing Octave with ECL. I think it's been we are running short of time, so I'll just move forward a bit for us. And here is the first code. Can we run MATLAB code in Octave? So I'd like to see the answer, just to know how audience are familiar with Octave. Yeah, just before starting going into the development of plugin or whatever it is. So just give just a brief introduction about Octave. What Octave is. So Octave is a scientific programming language used for numerical computation. It's an open source GNU project and started in 1988 and the first version was out by 1994. So one of the main reasons Octave started was just to replicate the functionality what MATLAB has and make sure that a lot of people use it. And Octave, like other languages, is a scripting-based language. We write queries, and Octave also supports user-defined functions, script files, function files, and mix files. So all are self-explanatory, and I just say what files is. Mix files are files which acts as an interface to C, C++, and Fortran. If you want to bring additional computation from those languages to the Octave, you can use mix files. So Octave has primitive types like logical, double, int, data containers like structure, cell array, and structure array. So I'm going to talk about this data containers in the coming slide. So this is about the basic introduction about the Octave. And I have few examples of the Octave queries. I can define functions. You can see there the second point says okay, define a function, and I can assign a variable with some values, and I can use the functions defined in the defined by the user. So moving on. So people who already work with ECL, who have used so many other embedded languages, probably thinking, why do I need Octave? What's the use of Octave? So here are a few points I'd like to mention just to appreciate why Octave can be used on a big data platform like HPCC. So Octave is a numeric scientific language which simplifies mathematical operations to a great extent. So if you see the modern day scenario, all the data that we get is a numerical data, or else if we don't get a numerical data, it can be a numerical data. So this is one of the reasons why Octave can be extensively used on HPCC. Big data, the inflow of data will be huge, and it will be mostly in numerical data. So that is one of the reasons why embedding Octave is necessary on HPCC. Octave functionality can be greatly expanded by the addition of packages or modules. Has a wide range of packages available like image processing, genetic algorithms, and audio processing. it's not just the usage of Octave doesn't bring the mathematical computation, but a lot of packages are available out there. As I mentioned, image processing is there, fuzzy logic toolkit is there, and even we have packages which support machine learning, data smoothing. Lot of packages are there which can be extensively used in using the Octave as an embedded language. My friends Surya and Akshay were talking about machine learning. Yeah, that's a different approach to design the machine learning model. Using Octave, you can also design the machine learning model. It adds in one more way of you designing the model on the HPCC. Octave has built-in linear algebra support along with the additional package for linear algebra. So if people are familiar with machine learning, so linear algebra is basic for machine learning. So to design any model that you need for machine learning, you can use Octave there. And of all the points I mentioned, the last 2 points are the most important. Octave is an open source product, and Octave supports MATLAB code. So MATLAB is an extensively used product in numerous fields. So you may be familiar with MATLAB. So MATLAB, to use MATLAB, we have to get a license from them. So, but Octave is an open source with the same functionality as MATLAB. So that's one of the reason that Octave can be used on a big data platform like HPCC. Moving on, this is a small note for all the users who want to use Octave plugin. The usage of Octave plugin requires pre-installation of Octave. The best recommended way to have pre-installed Octave is to build from the source. You can get it from ftpgnu.org, and then the version the plugin development was done was 5.1.0. The Octave version was 5.1.0. So make sure that you have pre-installed Octave and build from source. Moving on, I'll just brief you about how the development of Octave plugin was made. I'm not sure about the audience how familiar they are with development or working of a plugin. So here is a brief surface that I'll try to make. Here we go. So Octave interpreter is the core of Octave environment. Initialization of interpreter builds all the necessary requirements for evaluating embedded code. So if you, as I said, Octave is a query-based language where you write each query. So what happens when I submit a query? Where does it go? So this is where it lands. Octave interpreter. So Octave interpreter is an object of which represents the Octave environment. It receives all the queries that you do, and it evaluates using the function called eval string. So which returns an object of Octave value. What is Octave value? Octave value is the universal representation of data in Octave environment. It can represent int, can represent string, all types of Octave types using Octave value. So how do the implement the plugin works? So I evaluate the embedded code within the Octave. I store it in a global variable, and then pass the variable among the methods of the wrapper class. This is how I extract the result from the evaluated code. So, and to bind the parameters, what I do is I build an object of Octave value, pass it to a Octave interpreter. In the Octave interpreter, I use a reference of symbol scope. Symbol scope maintains something called symbol table, where all the variables are there, and then I append the variable to the variables, append the variables to the symbol table, and then which adds the variables to the working frame, and then I evaluate it and then clear all the things. So plugin development is not about the evaluation of the embedded code, it's about the passing of data from Octave to ECL and ECL to Octave. When I said I evaluate the code and store a global variable, store the result in a global variable, that means I'm getting the data, passing the data from Octave to ECL. When I say I bind the parameters, I'm passing the data from ECL to Octave. I hope all the people, all the audience get a brief idea about how it works. And moving on, the last point to add on, exception handling is done using maintaining the error stream. This is because of the reason Octave environment directly writes the error to the error stream, so we have to maintain error stream and then handle the exceptions. So here I'll not explain about these things. And if you see there, the two tables there, when I say I pass the data, what type is mapped to what. So here's a few examples of it. If you see the right table to the right, you can see the set of string is mapped to char matrix. You may question why is string mapped to char matrix? Why isn't it mapped to string vector? So by Octave 5.1.0 version, we don't have any support for string matrix or string vector. So when I declare a string variable in it, it is a character vector. So the set of string is mapped to char matrix, where each row in a char matrix represents single string in a set of string. So that's how it is. And record is mapped to a structure. So as I said, structure is a data container similar to the record. Elements of the structure are accessed using the field names. And yeah, it is one-to-one mapping. It's proper mapping from record to the structure. And dataset is mapped to two types, structure array and matrix. I'll talk about why I map two types of data to dataset. So we'll see about that in our next slide. So as you see, Octave plugin doesn't support data and a Unicode type. It doesn't support set of records and set of datasets. And for the usage of matrix, there are few restrictions. We have few examples in the coming slides, and we'll see how we can use those things. So record, dataset, and matrix. So if matrix is a basic type in Octave, so all the operations that are made in our Octave use matrix as a basic type. So it's a first class object in Octave. So to define a matrix, the equivalent ECL definition will go like this, where the record template has a set of real or set of integer as a field, and this is the only type that maps to matrix. So this is how we can deal with matrices in a embedded or in Octave plugin. So we can't use set of char within that thing. The reason because it will map to a multi-dimensional matrix, which is not supported by the plugin. And matrix there are few restrictions of it. The next 2 points just say about the restrictions I'll talk about in the coming examples. Before going to the examples, for all the users who want to use the plugin, so whenever you want to get an output from the embedded code, I ask you to explicitly mention the return value of the last statement. The reason because to support conditional statements and iterative systems, there are some restrictions, and sometimes the output that we get on an Octave command from our Octave shell is different than what we get using eval string of Octave interpreter. So if you want a specific output, please to write explicitly the return statement at the last. So here's the first example. It just shows you a conditional block there, and then I get a Boolean output. I pass an integer to it. This is a simple example. I just wanted to show you that conditional blocks can be used within the embedded code. And then moving on, if you're not sure, if you're confused by the mapping of data type, you can actually check what type of data type is mapped to what type in Octave. So there are a function called class of x which gives the description of the type. So I have passed unsigned x. The class x represents a string which says x is of type unsigned integer. So that's what the output is. These examples show that you can use the predefined functions within the Octave. That's pretty much it in these examples. As I said, Octave minimizes or simplifies numerical computation to a large extent. So if you can see there, I am multiplying two vectors element-wise multiple Hadamard product, where the ith element of A is multiplied with the ith element of C. So if you use any other languages, you have to put for loop, then move through it, then store it in a variable and get it. It will be like 4-6 lines of code. If you can see there, the simplification is just 4 characters of code within an Octave. So Octave simplifies mathematical operation to a large extent. The coming slides explain there's a record definition over there. I have a record which has fields real C, real S, real T, which are mapped to cause, which are real cause, real sign. Those are the values. If you see the below definition where I have say generate trigonometry, I have passed a value to it. I have generated the values and stored that in a structure. So structure is mapped to a record. So if you see the last statement, I have explicitly mentioned the return value as X. That's the reason. That's one of the important condition while using an Octave plugin. So you have to explicitly say mention what type you want as an output. And moving on, here is a example how you can use matrix. Matrix is defined using a set of real data record templates. I can pass the matrix to the working frame only if it is a part of another record or a part of another data set. We can't directly pass the matrix to the working frame. The example brief you about that. You can go through it. And the next slide says we can get the Octave matrix output from the embedded code. The restriction is only for sending the parameters into the working frame. There are no restrictions of getting any output from the embedded code. So the last example shows about a data set. So it's just a data set where it's mapped to structure array. So I have sent a structure array to the working frame. I have manipulated the data and returned it. So here I just finish it by a small quick poll. What type of array indexing does Octave have? Octave use. I'll look into this. I'll be waiting for this answer. It's an interesting question for all of you. And then I'll just conclude it. Say Octave plugin adds one more language to the list of embedded language supported by ECS. Octave brings extended functionality to the HPCC system. It can be used extensively on big data. So before concluding it, I'll thank everyone and HPCC Summer Internship Committee to give me an opportunity to work on the work for HPCC system. Thank you.
All right, thank you so much. This has been very informative. Let's take just a quick moment and look at your first poll question, which was, can MATLAB code run in Octave? And 66% said yes, and 33% said no. So, Saptak, what is your answer?
The answer is yes, you can run MATLAB code in Octave.
All right, perfect. And, well, we've got your last one right here, which is what type of an array indexing does Octave use? And this is a little bit of a trick question, isn't it? I know people are still answering it, but would you mind giving us the answer real quick?
Yeah, the answer is one-based, and people who got marked it as one-based, they are absolutely right.
Awesome. So all the people who answered it actually answered it correctly. So that's fantastic. All right, we have time here for one really quick question. And that question is, can you please explain about the usage of the external package?
Yeah, it's Octave. The usage of Octave can be extended exponentially by the usage of additional external packages. So the how I use an package within an embedded script is simple. So you get the package on your system, and then as you, it's similar to the way you write the script files. You define, you load the package into the interpreter, you use all the functionality, and you unload it. So it's simple as it. So when the definition starts, when the embedded code starts, you load it, you use it, and then you unload it and return whatever the value you want. I think that's how you use an external package.
All right, wonderful. Thank you so much, Satvik, and really to all of you gentlemen for joining us today. Your presentations have been so informative, and we've loved having you here as our interns. So if you would like to join us for a future Tech Talk, we would absolutely love to have you reach out to us at techtalks@hpccsystems.com. And I know that we didn't get a chance to get to all the questions today, and we had a lot of questions. If you would like, you can reach out directly. There's some contact information, I think, for each one of our speakers, or you can reach out to us at techtalks@hpccsystems.com, and we'll make sure that we get your answer back to you. And also, as with all of our Tech Talks, we've got the wiki, and you can access this again from our navigation. Just go to the drop-down that says Tech Talks. So I believe it's Community and then Tech Talks. And that's where the wiki is. All of our past speakers, these speakers today, all of the information will be there. You can also search by subject. All right, our next episode is September 17th, so mark your calendars today. And thank you very much for visiting us. Have a great day.